Okay. So we're going to start today. We'll introduce this topic. Like I said, we'll have a couple more days to do it next week. That's great. It's just that was weird. That was the computer. That wasn't the projector. I definitely need to restart this computer. It's not happy with me. You can see by the spinning cursor. But luckily, everything that's really happening is happening on the tablet. So anyway, back to what I was saying. We'll have a couple days to do this one. We're going to look at two different things. We're actually going to learn how to solve limits as x approaches infinity. We haven't done that yet. It's a whole different process. When that x goes to infinity, you're going to think in a totally different way. Because we're not looking at approaching a value. We're thinking about plugging giant numbers into our function. Before we jump and learn how to do that, there are some limits that we just need to know. If you think about when you get like translations or moving around, stretching and shrinking functions in Algebra 2 or in pre-calc, when we do things to functions, we have things called parent functions. That's kind of what I have up here. These visuals should be in your head by the time the test comes in May. We are going to look at logarithm graphs, exponentials, the 1 over x, and then general polynomials. So I started out with everybody's favorite, the logarithm. The thing that probably makes the least sense of anything that you've learned in math, just the way it is. But the logarithm. It doesn't matter what your base is, the graph always looks the same. We really use, when it comes to logarithms, we will primarily use ln. We'll use the natural log. We're going to talk about why we like this base e so much in a lesson in the next unit. But it really does. For all of the calculus that we do, everything is just easier if your base is e, so that's what we're going to focus on. I have just a generic log graph up here because they all look the same. If you change the base, you just end up stretching this graph, stretching or shrinking it vertically, but they all do look the same. Logarithms can't have negative numbers plugged into them, right? If you look at that graph, I have the y-axis all the way to the left because this graph only gets positive. You can only plug positive numbers into a logarithm. We talked about that when we were doing domain. So the two limits that we need to know about logarithms is what happens as you're approaching zero. And what happens as you're approaching zero is you have a vertical asymptote. You can only approach zero from the right because there's no graph on the left. So the limit as x goes to zero right of any log is negative infinity. You have an asymptote, and that graph is shooting down into the negatives. That is not a limit at infinity. That's just an x value that you need to know the limit of. Most of these will be limits at infinities, but the log graph kind of has both of those things. Logs grow, and they grow forever. There is no bound to how big you can make the log function. The only problem is it takes really, really big x's to get kind of big y values. So log grows really slowly. The further the graph goes, the flatter it looks. But if you wanted to get to 1 billion, you could scroll and get there. The thing is, your x value would be significantly bigger than 1 billion. That's kind of one of the properties to know about the log graph. It does grow forever. So as x goes to infinity, I can get as high as I want from that graph. That limit is going to be infinity. Can I get 1 billion out of a log function? Yeah, you need a big number, but there's no bound to how big you can get out of the log. There are 2 points on every log graph that you should know. So a lot of times on a non-calculator question, you may need to evaluate a logarithm, but they're probably going to give you one of these 2 points. If you plug wait, I'm make sure I get this right. In my brain, I was about to say the wrong thing, so I just have to reset. This is saying, what do I have to plug in to get 0 out of my logarithm? And that is the base. Yeah, the base. Yep. Yeah. That is an A, yeah. I'll make sure I'm right here. I'm like blanking. My brain's not, and I know this. I did this with the other group, and I didn't have to think twice about it. Yeah, it is. Maybe that's, yep. I'm going to say that whatever these points are, they are the opposite on the logarithmic graph. So this would be, yeah, no, I am wrong. Yep, I am wrong. That's not A0, that's A1. That's 1, 0. There we go. Yep, 0, 1. Yes, yeah, got it. Okay, all right. Yeah, my explanation wasn't making sense in my head, so that was telling me wrong. So again, I'm telling you need to remember these things. I'm telling you that sometimes I forget these things. I'm good in math because I can always figure things out if I have to. I think that's just an observation. Like if you can, the more you can figure things out, the less you have to remember. But then you have the legwork of having to figure them out. So if I say the log of base A of 1, I'm saying, what do I have to, what do I have to raise this base to get 1? And it doesn't matter what that base is because that answer is 0. What do I have to raise 7 to so that my answer is 1? 0. What do I have to raise 5 to so that my answer is 1? 0. What do I have to raise e to, some weird number, to get 1? That answer is 0. And that's the question that logarithm answers. That's why I always bring that up. That's how I remember it when I haven't looked at it I looked at this 3 days ago with BC, but usually I would say a long time there. The other thing that's always on every log graph is the base itself. So this is a similar question. What do I have to raise my base to get my base? What do I have to raise 7 to so that my answer is 7? 1, right? So it doesn't matter what your base is. Those two things will always be on every log graph. So yeah, that is our logarithm. You know, it does answer this question. It's a bit of a weird question, and you kind of have to move the numbers around in your head to ask that question, but it does answer the question. What do I have to raise my base to get 1? That answer is 0. What do I have to raise my base A to get the same thing? That answer is 1. Okay, our next graph is an exponential graph. These two things are inverses. So they are, they're not just a flip. They are a diagonal. If you were to draw the line y equals x and then reflect across y equals x, you'd have that graph. So they have a lot of things in common. And it does turn out that these 2 points are flipped versions of each other. So much more straightforward. What do I have to raise, or sorry, what happens when I raise a to the 0th power? I get 1. And then this is going to be a flip of this point, 1 comma a. What happens when I raise my base to the 1st power? I don't change it, 1 comma a. A to the 1st is a. 1 comma a. This is always under the assumption that we're taking a number bigger than 1. This graph would look different if I had 1/2 to the x power. I'd have something different going on there. This is taking a whole number, or a number bigger than 1. I shouldn't even say whole number. A number bigger than 1 and raising it to a power. As x goes to infinity, exponential growth, an overused term, you can get it as big as you want. It's not hard to get a big number out of an exponential graph. You start raising to the 3rd, 4th, 5th, 7th power, you start getting really big numbers. That's why sometimes people overuse the term exponential growth, because we've got things growing really fast. But how about as x goes to negative infinity? What happens when I plug really big but negative numbers into an exponent like that? A to the negative 3rd power, a to the negative 5th power. What's that? It goes to 0. That negative power drops our a into the denominator. So now those really big numbers are showing up in the denominator, and we're basically just taking 1 and dividing it by a huge number. So we have a horizontal asymptote, a to the x or e to the x. Any base bigger than 1 to the x is going to go to 0 as we go to negative infinity. Much along those same lines, but simpler, when we look at 1 over x, this is what the graph of 1 over x looks like. It's got a vertical asymptote at x equals 0. I don't have that listed here. Maybe I should. It's got a vertical asymptote at x equals 0. It's got horizontal asymptotes at y equals 0. It is kind of like a mirror image of itself, kind of across this diagonal line here. But on both ends, you are asking yourself, what happens when I divide 1 by either a giant number or a giant number that happens to be negative? And the bigger your denominator is, the closer you get to 0. So both of these limits are 0 for that reason and the fact that we have a horizontal asymptote. Let's, while we're here and we have the space, list the other asymptote. Zero left and 0 right of f of x. We can do these from the graph. We could make a sign chart, be a very, very similar sign chart to the one that I've written in pen up here. As we come in from the left, it's negative infinity. As we come in from the right, it's positive infinity. So negative, positive. All right. And then the last thing we're going to look at are just single term polynomials. X to a power depends on whether that power is even or odd. I believe I have x to the 4th graphed here. You'll notice that this looks a little bit flatter than like a parabola from x squared. That part doesn't matter, but I say that just so that you realize that, you know, whether it's x squared, x to the 4th, x to the 6th, x to the 8th, if that power is even, you get a shape that looks like that. The higher the power is, the flatter this little piece ends up being, but you still end up with basically the, a U-type shape. And in both directions, plugging a positive number in that's big or plugging a big number that happens to be negative in, and then raising it to that power, that's going to give you an even larger number that's positive. So in both ends of this graph, infinity and negative infinity, we're shooting up forever. So those are both infinities. However, man, this typo, I just can't get rid of it. This is probably the 15th time in my life I've corrected that typo in front of students, but not ever in the actual document. This represents an odd power, and it should make sense. Really what happens is, instead of these numbers on the left being positive, because you're multiplying 3 negative numbers by itself, they end up negative. But that means that the negative infinity limit goes to negative infinity. So again, the expectation is that you guys have all of this in your head. It is, but it is the expectation. Not all of it's brand new. None of it's brand new. Some of it's stuff that should be a little bit more familiar. I feel like this, of anything, should be the things that you kind of should be like, oh yeah, that makes sense. I kind of knew that. Log, that's not expect. That's probably why I have it first. I went through the hardest thing first. And you guys definitely graph 1 over x in Alg 2, and I'm assuming pre-calc, but I've never taught it. Okay. All right, let's take a look at some limits. So what happens when I start messing around with things? This first limit is kind of a direct look at e to the x, except the problem is I don't have my a less than 1. This would be what happens. I'm actually taking, when I take e and I raise it to the x power, I'm putting e to the x in the denominator. And because of that, I really am raising 1 over e to the x power. That's really what's going on there. I don't want to rewrite it that way because that's not how I'm going to solve it. But I am taking the fraction 1 over e and raising it to the x power. So it's not the same graph from the top, because 1 over e is 1 over 2 point something. That's smaller than 1. But our rules still apply here. I know a limit for e to the x, but I have e to the negative x. Negative x is the argument of that function. So I don't want the limit as x goes to infinity. I want the limit as negative x goes to something. X goes to infinity means I am plugging bigger and bigger and bigger and bigger numbers in for x. So what's negative x going to? Negative infinity. Yeah, negative infinity. I'm taking those same numbers, but I'm dropping a negative sign in front of them after I look at them. So that's going to be negative infinity. I'm in the same situation I have been in the past where I've got my argument and my approach matching, so now I can rewrite. Instead of the limit as negative x goes to negative infinity, I'm going to rewrite the limit as x goes to infinity of, negative infinity. I got ahead of myself in my brain. All I'm doing is changing the variable, so nothing else gets to change. Boom. I don't have my equals on the wrong side. Okay, so that's the same process we always do. Our approach and our arguments don't match, so I make them match, and then I simplify it up, and that's a limit I know at the top. As x goes to negative infinity, e to the x goes to, what does it say on your paper? It's for a to the x. A to the x applies. Yeah, 0. Yep. I am taking e and I'm plugging giant but negative numbers into it. So I'm raising it to huge negative powers. Those negative powers are dropping it into the into the denominator. I swear I used to have better palm recognition there. Okay. You can think through this straight from the beginning. This question that I'm answering here, you can see that from that limit. I am plugging giant numbers into e to the negative x. So in the end, I've got my e function being raised to giant negative numbers. You can get to this limit directly if you know how to think through these things, but that's the math behind it. My approach doesn't match, so make it approach. If x was going to infinity, negative x is going to negative infinity. Just clean it up. Change those both negative x's to x's. Okay, same thing with this one. This one, I don't really have an argument change here, so I really just have to think it through. I am putting giant but negative numbers into x cubed, and then when I'm done, I'm multiplying that by negative 4. So what happens if I take a giant negative number and cube it? Is it still giant? Yeah, it's even bigger. Is it still negative? Yes. So I've got a giant negative number that I am then multiplying by negative 4. Then it's positive. So this answer is positive infinity. Yep, infinity or positive. I was listening for positive infinity, but when you said infinity, that's absolutely correct. All right. Our last one leads into the next part of this. We've got the limit as x goes to infinity of 3x minus 5x squared. When you have polynomials and you're talking about putting giant numbers into them, think about it. We're looking at what happens to the result. Take a not giant number like 100. 3 times 100 is 100. But here I'm squaring that 100. So instead of 2 zeros, I got 4. So I've got 300 minus 50,000. Yeah, and I don't care about what that answer is. Yeah. And that answer, I don't care. I want to look at those two numbers. 300 minus 50,000. It's going to be 49,000 something, right? But it's still going to be pretty big. It's going to be on the order of 50,000. It's near 50,000. Now imagine you do that with more zeros. Take a number like a million, 6 zeros. You're going to have 3 with 6 zeros after it. But when you square it, you're going to have 5 with 12 zeros after it, right? So when you go to subtract those, you've got 5 with 12 zeros after it, and then 3 with 6 zeros after it. you're still going to be really, really close. Like this number is the one that matters, right? If you want to know what ballpark you're in, this is the number that matters. So when we're talking about exponential growth, we can actually get rid of things that are growing slower, and we look for the thing that's growing the fastest. So this limit, we can get rid of that 3x. It turns out it's going to be exactly the same as the limit as x goes to infinity of just the x squared term, negative 5x squared. Can't lose the coefficient. If I put this would be, I'd have to mess around with it, and this is probably where we'll start off on Monday. If I put these two graphs in Desmos, for small numbers, those two lines are going to be very different from each other. They're going to have a significant difference because I am doing a subtraction problem here. But if I zoom it out and get all the scale and stuff right, when I start getting to those numbers like 1,000, 1,000,000, 100 million, and you can go, and those are small, still small numbers because I could put 1,000 zeros after a 1. Those graphs are going to be so close that these limits, basically, you're going to say these are basically the same function. They are so stinking close, they're doing the exact thing. So this is going to be what we'll be focusing on in the next section on Monday. Basically, we're going to say fastest growing function. Take the fastest growing part of this, the x squared, and just find that limit. Again, giant number into x squared, still going to be giant, still going to be positive, but then multiplying it by negative 5, negative infinity is your answer there. Cool. All right, so that is where we will pick up on Monday. We're going to square our giant number, but then we're going to multiply it by negative 5. Yeah, so that's the limit of x squared. The negative 5 affects that. Yeah, the negative 5 affects that. When we look at this graph, we're going to see that our graph, well, let me just, I can do this without, we don't even need the giant numbers. It's a good question. I don't want to know, I want a new one. I only knew how to make a new graph. All right. What is it, 3x minus 5x squared?
One nation, under God, indivisible, with liberty and justice for all.
Yep. All right. So here's the function we're looking at. And if you think about what we're doing here, we're trying to figure out whether this graph shoots off the bottom or off the top. Because that 5x squared is negative, you end up with a downward facing parabola. It's shooting out the bottom. So you do have to, you use that to figure out what x squared is, but then you have to take into account what it's being multiplied by.